Today in the Operating Systems course, we are going to cover demand paging. Demand paging is most commonly used virtual memory management system. It is based on the locality model of program execution. Locality is defined as a set of pages actively used together. As a program executes, it moves from locality to locality. A program is composed of several different localities that may overlap. For example, a small procedure when called defines a new locality. A while do loop while being executed defines another new locality. In demand paging, programs reside on a swapping device, typically a disk, commonly known as the backend store. When operating system decides to start a new process, it swaps only a small part of this new process, maybe a few pages into memory. The page table of this new process is prepared and loaded into memory, and the valid-invalid bits of all pages that are brought into memory are set to valid. All the other valid-invalid bits are set to invalid, showing that those pages are not brought into memory. In demand paging, if the process currently executing tries to access a page which is not in the memory, a page fault, shortly PF, occurs. In case of a page fault, operating system finds the desired page on the backend store. If there exists no free frame in memory, operating system chooses a suitable page as the victim page and swaps it out to the backend store. Operating system changes the valid bit of the victim page in page table to invalid, indicating that it is no longer in memory. It swaps the desired page into the newly freed frame, modifies the frame table, and sets the valid-invalid bit of the new page to valid. Then executing process is allowed to go on. In demand paging, page fault service operations can be summarized as follows. Suspend the process and do context switch. This is the first operation. Check the address and find a free frame or a victim page. Again, first operation. Swap out victim page to secondary storage. This is a slow operation. Swap in the page from the secondary storage. This is another slow operation. Context switch for the suspended process and resume its execution. This is a fast operation. In servicing a page fault, time is spent mainly for swap out and swap in operations. Time spent for others are negligible in comparison. Virtual memory can be implemented in the form of paging systems, paged segmentation systems, this means variable size pages. However, segment replacement is much more sophisticated than page replacement, since segments are of variable size. The performance calculation of demand paging is as follows. If there is no page fault, effective access time is same as effective memory access time, EMAT. So, effective access time, no page fault is EMAT. If there's a page fault, we have effective access time, page fault, which is equal to page fault service time plus effective memory access time. So this can be negligible compared to the page fault service time. This is approximately equal to page fault service time. In general, effective memory access time is very small compared to page fault service time, hence it can be ignored if there is page fault. Let P be the probability of page fault to occur. P is a value between 0 and 1. Then the effective access time can be calculated as follows. Effective access time is P multiplied by effective access time in the case of page fault plus 1 minus P multiplied by effective access time in the case of no page fault. In the previous slide, we have seen that in the page fault case, effective memory access time is almost equal to page fault service time. So P is multiplied by page fault service time plus 1 minus P in the case of no page fault, then effective memory access time is constant. So 1 minus P multiplied by effective memory access time. So the result is effective access time constant also page fault service and its probability. Here is an example. Effective memory access time for a system is given as 1 microseconds. And the average page fault service time is given as 10 milliseconds. Let the probability of page fault to occur is 0.001. Then effective access time is, this is P multiplied by the page fault service time, which is 10 milliseconds, plus 1 minus P multiplied by effective memory access time. So we have convert this millisecond to microsecond, so multiply by 1000 plus here 1 minus 0.001 is 0.999. This can be approximately taken as 1. So we have here 10 microsecond for the page fault case plus 1 microsecond for the no page fault case. Totally it makes 11 microsecond. Notice that for page fault service, most of the time is spent for swap out and swap in operations. In order to reduce page fault service time, a special bit called the dirty bit can be associated with each page. The dirty bit is set to 1 by the hardware whenever the page is modified. That means it is written into. When we select a victim by using a page fault replacement algorithm, we examine its dirty bit. If it is set, that means the page has been modified since it has been swapped in. In this case, we have to write that page into the backend store. However, if the dirty bit is reset, that means that the page has not been modified since it was swapped in, so we don't have to write it into backend store because a copy in the backend store is valid. Let the probability of a page being dirty be D. In this case, effective access time becomes here with the page fault occurring probability, we are multiplying, and here is the probability a page is not dirty because we are taking 1 minus T, and we are multiplying it with swap in because swap out is not needed in the page fault service time. We are constant only swapping. However, if the page is dirty, then with D we are multiplying swap in plus swap out. So this is corresponding to on the average what is the page fault service time. It is multiplied by the page fault probability plus we have 1 minus P. That means that page fault is not occurring. In these cases, we are considering only the effective memory access time. So this is the effective access time if dirty bit is constant. For choosing a victim page, we have some page replacement algorithms. These are optimal algorithm, not recently used algorithm, first in, first out, shortly FIFO algorithm, second chance algorithm, clock algorithm, least recently used LRU algorithm, working set algorithm, and working set clock algorithm. A page replacement algorithm determines how victim page to be replaced is selected when a page fault occurs. The aim is to minimize the page fault rate. Efficiency is evaluated by running the algorithm on a particular string of memory references and computing the number of page faults. Reference strings are either generated randomly or by tracing the paging behavior of a system and recording the page number for each logical memory access. Consecutive references to the same page may be reduced to a single reference because they won't cause any page fault except possibly the first one. So suppose that these pages in the memory are referenced in a program. These are 1, 4, 1, 6, and here 1 is repeated 3 times. So this can be reduced to a single one, memory reference 1 and 3. So here, notice that we have a single reference for page 1. We have to know the number of page frames available in order to be able to decide on the page to be replaced. Optionally, a frame allocation policy may be followed. In the optimal page replacement algorithm, the victim is the page which will not be used for the longest period. For a fixed number of frames, optimal policy has the lowest page fault rate among all page replacement algorithms. But the problem is that optimal algorithm is not possible to be implemented in practice since it requires future knowledge. We do not know which pages are going to be accessed in future without executing the code. It is used for performance comparison. Example, assume we have 3 frames for the process. Consider the reference string below, 5760717, etc. Show the content of memory after each memory reference if optimal page replacement algorithm is used. Find also the number of page faults. So here the page references are shown. We have 3 frames in the memory. When we are going to load a page into the frames, we are saying that there is a page fault. And here there's a reference to page 5. It is not in the memory, so it is loaded into the frame 1. Suppose that all these 3 frames are free, and this is the first page fault. And then there is a reference to page 7. We have 2 free frames. It may be loaded there. So suppose that it is loaded to the frame 2. Then there is a reference to page 6. It is loaded here because this was free. And then comes a reference to page 0. And page 0 is not in the memory. Because of that, one of these frames should be chosen as the victim. And in this algorithm, the victim is the page which will not be used for the longest period. So we are looking to the future. And let's check when these pages are going to be used. Here we are checking 5 is not going to be used in future. 7 is to be used here in near future. 6 is also not going to be used in future. So we can choose either 5 or 6 as the victim. And let's choose the first one. So this is the victim to be removed from the memory. So 0 is loaded into that page. This is swapped out and 0 is swapped in. And notice that again, 0 is not in the memory. This is another page fault. Then comes a reference to page 7. It is already in the memory, so there is no need to choose a victim. And the content is the same, there is no change. 7 was in the memory, and there is no page fault here. Now there is a reference to page 1. Again, it is not in the memory. One of the pages is going to be chosen as the victim. And let's check them. 0 is going to be here, and 7 is going to be used before 0, and 6 is not going to be used in future. So 6, this is chosen as the victim. So we are going to load this new page into frame 3. This is another page fault because this was not in the memory. Page fault 5. Then comes a reference to page 7. It's already in the memory. So there is no change in the memory content and there is no page fault. Then comes a reference to page 2. And we are going to choose one of these as the victim. The reference to 0 here, 7 is there, and 1 is here. So the page which will not be used for the longest period is 7. So 7 is chosen as the victim, and 2 is going to be loaded into that location. This is another page fault because this one is swapped out and the new page is swapped into the memory. It was not in the memory. And there's a reference to page 0. It is already in the memory. There is no page fault. Now there is a reference to 1. It is again in the memory. A reference to page 7. It is not in the memory. We are checking which page is not going to be used for the longest period. 0 is going to be used here. 2 will not be used in future. And 1 is going to be used here. So 2 is chosen as the victim. Page 7 is loaded instead of that page. And this is the 7th page fault. Page faults are here. There was a page fault here. And this is the page fault 7. Then comes a reference to page 1. It was already in the memory. There is no page fault. A reference to page 0. Again, there is no page fault. So the total number of page faults in this example with 3 frames and with these page references, we have 7 page faults with the optimal page replacement algorithm. And notice that this is the possible lowest number of page faults. Because we are using future knowledge, in practice this is not possible, but we are using this one, this knowledge in order to find out in the best case what would be the number of page faults with this number of frames. According to the given information, this algorithm generates a page replacement scheme with 7 page faults.